Hello, dear viewers. Welcome to the part 4 of the lecture series on weldability of nickel and nickel based alloy. Well, I personally feel that the schematic with which we cast, stopped, and discussed requires more explanation because this schematic provides many valuable insights into understanding the solidification, liquefaction cracking, and ductility deep cracking. Well, if you closely look at the schematic, you would see that this ductility versus temperature curve is more or it is very much sharply decreasing in the brittle temperature range, particularly in this pink colored zone, right? Because it is the immediate zone to the weld pool, molten weld pool, and where obviously liquid film is responsible, which is actually wetting the grain boundary. So under the cooling stresses, the strength or the ductility of the grain drops so severely that the material is no longer able to withstand this stress and develops cracks, right? So this is the solidification cracking, most of the time occurring in a weld metal, and liquefaction cracking, most of the time occurring in a heat affected zone or between fusion zone and heat affected zone. Okay, next, and it is between TL and TS. Remember, it is between temperature of solidus, temperature of liquidus. Fine. Just look at this purple color zone, which is just below the solidus temperature, and when the welding is in action and wherever the temperature is somewhere around half or quarter to the almost approximately quarter to the solidus temperature, so 50% or 70% to the solidus temperature, then the ductility drops and we have a ductility deep cracking, and this zone is particularly experiencing a elevated temperature where the strength drops or the ductility drops, and in this temperature range. So these are the main two issues, and remember here ductility deep cracking again, it is we will discuss in subsequent slides, but where multiple pass or for joining the thick section where multiple pass are employed. Also, most of the time precipitation reactions are taking place, and these precipitation reactions are responsible for lowering the ductility, and we have a cracking issues, and again strainage cracking that may happen during the post-wear heat treatment processes. We are going to discuss in detail in our next slides, in our subsequent slides. Okay, so to move further, this is a capture from the research article authored by Jesse Lippard and Clark WAT. Just for the sake of explanation, is a epitaxial grain growth. You would see right? You would see this kind of grain growth. uh, this is a weld center, so you know this is a grain boundary. Literally you can see a grain boundary. It's a elliptical shaped grain, and this is the solidification grain subgrain boundary. It is the boundary between the grains, so it is a solidification subgrain boundary. And this one is the migrated grain boundary. Migrated grain boundary is one which has been shifted from its original place, and due to the orientation of these grains, and you would see this liquid film, or it is molten metal is about to freeze, right? Okay. uh, this zone is more susceptible sometimes weld center cracking, where the or segregation of low melting point elements into the grain boundary or subgrain boundaries, most of the time responsible for solidification cracking. Okay, so here is the example. If you look at the picture, it is a 304 stainless steel deposited by 52 filler metal 52, which is a inconel filler metal, and you would literally see a crack, right? That forms along solidification grain boundaries, and it is due to presence of liquid films which is wetting austenitic grain boundaries, and the wetted grain boundaries are separated apart from each other under the restraint present. How to avoid weld solidification cracking? Well, there are two strategies. First is to minimize restraint. Minimization of restraints will again depend on the joint design, because we will see in subsequent slides that the uh, nickel based alloy are rather sluggish and less viscous than less fluid than stainless steel metal, so they are provided more included angle, so joint design has to be taken care of. Secondly, using base metal in solution annealed condition, so there will be less restraint or less residual tensile residual stresses and increasing number of passes. When you increase number of passes or multiple pass, it will reduce the restraint, because simultaneous stress relaxation or simultaneous stress relaxation will take place. Or second strategy is by using cracking resistance filler better. Either you flux coated or bare electrodes with SMAW or GTW or GMAW electrodes, nickel chrome moly 3, that is not alloy 625 filler, nickel chrome moly 4, Hastelloy C20C76 filler, or Ni1 or nickel 141 filler metal. So these filler metals are designed to avoid weld solidification cracking, because uh, they would backfill the any crack and provide resistance to solidification cracking. Now in this figure you would see a HSL liquefaction cracking in alloy 718. Here it is because of the constitutional liquefaction of niobium carbides. Had I mentioned you in my previous class that because of NBC constitution's liquefaction, whenever the niobium is added as a strengthening element in a precipitation hardening alloy, uh, is also causing a cracking issues in a liquefaction HSL area known as HSL liquefaction crack, and this you would see between these two right arrow, right? And